All right, welcome to density, and a physical property of matter. Uh, Density is the physical property of matter which describes the relationship between something's mass and its volume. So here's our density, and it's equal to the mass, which we're going to measure in grams, over its volume, which for a solid substance, it's in cubic centimeters. For a liquid, we report it in grams per milliliter. And for a gas, we report it in grams per liter. And please note that 1 cubic centimeter is equal to 1 milliliter. Mass can be easily determined using a balance, but volume is not so easy to determine. You can pretty simply measure the volume of a rectangular prism by measuring our length, our width, and our height and multiplying them together. And if you measure it in centimeters, then you're already in, once you multiply them, you're already in cubic centimeters and you're done. Make sure when you measure that you pay attention to your ruler, that you start from the actual zero. Some rulers don't have the 0 point on the very end because they can get like dinged, you can lose a corner. So make sure that you're measuring that first centimeter. You start at where it'll actually be a little mark that says 0, 1, 2, or start at 1 and just subtract 1 out, also fine while you're doing this lab. Another method to do this, if you have something that's, say, an irregular object or a bad ruler with a big ding on the front, is to use liquid displacement. Liquid displacement, so we have our irregular object. We have a graduated cylinder, which is a measurement device. A beaker would not be appropriate for this. A beaker is for storage of liquids, not for measuring them. So we put it in a graduated cylinder, and we'll say we have 10 milliliters in our graduated cylinder to begin with. We add our object, and the water level rises. And let's say it rises to 13 milliliters. So 13 minus 10, our object has a volume of 3 milliliters. It's equal to the amount of water that was displaced. The third method to determine this is one that you might not be familiar with yet, the Archimedes method over here. So objects that are in water are lighter than objects in air. They have the same mass. The mass doesn't change, but their weight, their apparent weight, will change. This is because the water pushes back on the substance, right? And it's with a force that's equal to the mass of the liquid that's displaced. And lucky for us, water has a density of about 1 gram per cubic centimeter. So we're going to use water. It makes our math a lot easier. This is temperature dependent, so we're going to have to measure the temperature in the laboratory to make sure that we have this accurate. But either way, we're still going to use this method. Once we do that, we have this scale here. And it's like a sliding scale like at the doctor's office. It's got a little hook on the end, and that's attached to the balance here. And then you hang your object on this hook. We give you a little string. You hang the object on the hook and record the mass. And then you put a beaker of water around the object, and it doesn't matter how much water is in the beaker as long as your object is fully submerged and not sitting on the bottom. And then you measure the mass again, and it'll appear to be lighter, and you will record the difference, and that will tell you the volume. So this is because when an object is floating, it's going to displace a volume of liquid with a mass equal to the mass of the object, but our object is going to be submerged, which means it's going to displace a volume of liquid which is equal to the object's volume. So the apparent loss of mass, like I said, is equal to the mass of the liquid, in this case water, that is displaced. So in this experiment, we're going to do all 3 different ways. The first thing that's going to happen is you're going to get a metal object. It might be stamped with a code, which will help us to identify it, but it might not. And either way, you need to record detailed observations about your object: size, shape, color, whether it feels light or heavy, and whether it has a code or not, and if it has a code, what the code is. All of this will help us verify that you got the density correct at the end. So you want to make sure that you put as much detail as possible, even if you have the code, for two reasons. One, with scientists, and detailed observations are important. And two, because maybe the code was written down wrong, or we might have two number 35s or something. So then after that, the next step is going to be record the mass of an object on an analytical balance, which is accurate to plus or minus 1 milligram, or 0.001 grams. That's our balance's accuracy limit. We're going to make some assumptions for part one. We're going to assume that this object is perfect. So there are no scratches, marks, dulled edges. None of this should give a significant enough change to the volume that at our measurement scale, it's going to matter. So that's fine, especially for part one, where you're just trying to measure an object with a ruler. The objects that we're going to give you are either going to be rectangular prisms like this, or cylinders, which is, vaguely this shape, but I didn't come here for my art skills. I'm sorry, you guys. It's not at all what a cylinder looks like. There we go. That's vaguely cylindry. So we know, remember that the volume of a rectangle is our length times our width times our height. And the volume of a cylinder is the radius squared times pi times the height. Also, remember that this equation is using the radius, not the diameter. Radius equals 1/2 the diameter. So this is, if we're looking down our cylinder, our diameter goes all the way across. That's a common mistake to make, so try to avoid that. Also, if you have a hollow cylinder, don't forget to, measure the large cylinder, that's the outer rim, measure the inner rim, and then subtract the volumes of the two cylinders. And that'll give you your volume. Then we're going to do water displacement, which is fairly straightforward. And the third way is we're going to be using this Archimedes method. There are, at the end, what you're going to have to assess which method is the best, or which method you find reliable. And a way that we describe reliability of scientific measurements uses words like accuracy, precision, and sensitivity. Accuracy is how close the measurement is to the accepted value or the theoretical value. So like the accepted value for the density of water, like we said, is 1.000 grams per milliliter at 40 degrees Celsius. So, are our measurements close to that? And are they kind of in the ballpark of 1, right? If we're throwing darts at the dartboard, are we close most of the time to this central point? And errors relating to accuracy are called percent error, and they are calculated by using the actual value minus the theoretical value divided by the theoretical value, and then you multiply that by 100% to get the percentage. That equation is actually up here. Precision is the repeatability of the measurement. So if you had 5 different people all weighing the same object, would they all get the same value? Probably not. But since the only difference is the people weighing the object, while all the other conditions are the same, like it's the same room, it's the same balance, it's the same object, well, yeah, but it's the same temperature in the room, the difference in the mass of the object will be very small and repeatable. Precision measurements give rise to an average deviation, and a percent deviation. And just, as someone with a little experience in the laboratory, you want your measurements to be both accurate and precise. But if I had an instrument that was giving me one over the other, I'd prefer precise because I can correct for that. But that's, neither here nor there. Also is sensitivity. So sensitivity is the scale used to measure something. Your ruler might measure to the nearest 1/16 of an inch. I hope not, because it should be in scientific units. But if you had a fine micrometer, it might read to the nearest 0.01 millimeter. There are benefits to using tools that are more or less sensitive. Ease of use, uh, how often they need to be calibrated, that kind of thing is a trade-off for sensitivity. So if I was like measuring a Mack truck on a highway, I don't really need to know that to the nearest milligram, so it doesn't have to be that sensitive. So with that, let's get started on the experiment. Usually, I know this is 171, but when you take 499, there's a part in the beginning where we answer questions about being a good TA and working with people. And because I might not see you this semester, or, well, I might not see you, I just want to give you a piece of advice that you should get from your TA and that we give to the new TAs and to the new students all the time. And it's just do your best and try. Always try. You'll make it through this semester just fine. I promise.
For part 1 and for part 2 and 3, you're going to be using the same solid for each part. You can use a rectangular prism or you can use a cylinder. So I'm just going to choose one of the solids, and I'm going to, for part 1, or method 1, just record the physical dimensions, so the length, width, and the height. Okay. So what you'll want to do is, with your chosen metal, first you'll want to record actually which metal that you have. So some might have a code, some might not. This one doesn't, so you'll just kind of record, the observation. It's heavier than, some of the other metals, so you can write that it's heavy, and you can record the color. It's like a yellowy, goldish kind of color. So we'll be taking the solid, and what we're going to do is we're just going to weigh it. And this will be our mass for all 3 parts. So 42.233. So for this experiment, you also want to record the temperature. So the temperature that we have right now is, 25.5.
Okay.
So now we're on to part 2. So part 2, we're going to try to find the volume of the solid by water displacement. So you're going to want to record, you fill this up with water first and record what the value is. So currently the value is 65.5. And what we're going to do is we're going to carefully, tilting it at a 45-degree angle, carefully place the solid here, and you'll want to let it slide towards the bottom. You don't want to drop it directly in, because then it might shatter the bottom, and that won't be fun. So then you'll just record the new volume.
That's a good technique, Matt. Flat on the benchtop with bringing your eyes level with it. That's great.
Yeah. So this is 70.5 milliliters. So the difference in the volume is the volume of our solid. So for part 3, for the Arrhenius method, what you'll first have to do is you'll have to dry your solid, because we're going to be weighing it in air first. But to do that, we need to tie it along a string. So the easiest method is actually making it into a loop over here. You're going to pass the string through here. I don't remember what this knot is called, but it's pretty easy. I mean, actually it's not that easy. So you'll pull it like so.
It doesn't matter if you use this method perfectly, as long as you get it securely tied.
Yeah, so like I did now.
Yeah, perfect.
I mean, you could also just try to tie it to the best of your ability, but eventually what you'll want is something like this, where the solid is kind of floating in air like this. Doesn't really matter that it's spinning, because it'll eventually just stop. know when that is. So when we want to do this on the balance, you'll see there's like this little hook here on these balances.
So this balance is like mostly balanced already, right? Like this is a pretty good balance.
Yeah, so it's kind of moving right now, but you should have these two lines, touching or fairly close to each other.
What if we didn't have a good balance? If it wasn't like perfect?
So that's a great question, Corey. So you can actually move this mass to try to align them perfectly, making sure that you record the initial mass and then removing that mass from every, like say from the mass of the solid, you'll take the total, subtracting the error correction.
Because it's like a constant now.
Yeah.
Yeah.
So that's what you can do. So anyway, for this hanging mass, we'll be using this hook and we'll carefully tie it onto this hook. Making sure, so what we're gonna do in, this next part is, we have this beaker full of water. You're gonna set it on here. So you wanna make sure that this solid doesn't, or won't touch the bottom of the beaker, but it won't be too high that it won't be fully submerged in the water itself. So we're gonna want like a nice level, like probably around like right here. And we're going to attempt to tie this thing in place.
And make sure when you do this in lab, you come with your solid already on the string.
Yes.
Don't stand here trying to tie a string while there's a line behind you. That is not a pro move there.
Yeah, see, like what I'm doing now is
You'll have people talking, distracting you. It's going to make it a lot harder to do your job.
Yeah. So, it might take you a couple tries. A little difficult, but just stay calm and don't try to rush it. So let's see. No, see.
Not touching the bottom.
Yeah, it's touching the bottom. So.
You can like loop it.
What?
Nah, never mind. You got it. You got this.
Yeah. So anyway, for those watching, you guys can skip ahead.
We're going to record this whole process. This also, future TAs don't have to feel bad about how difficult this is. It seems so simple.
The thing is, I've done this so many times, but it's still difficult. Yeah, no, it's still low.
I'm going to pause and we're gonna get this.
So once you have your metal hanging, and at a proper level, you'll notice that now these lines are no longer, against each other. So we're gonna have to adjust the mass of this triple beam balance to get them aligned again. So let's try that out. Okay, so and we've taken the mass of this on the balance, so what was that, 47?
Good thing we wrote it down. It is
Yeah.
close to 47.
Okay, so that's where we're gonna do like the ballpark area. So 40, not heavy enough. 50, too heavy. Now if it's like all the way down at the bottom, it means that there's too much mass on this side. So 40 is good, and then we'll move this over to, let's see, 7. Oh, interesting.
Still a little too heavy at 43.
Yeah, which is fine.
Yeah. So that's what you want to do. You want to move it until it's like, oh, it's too heavy, and then pull it back and see. Is this going to nail 42 even? That's crazy. No, you got it all the way over to 1 gram, so that makes it 43. Right? Yeah. Your smallest one's all the way to the right.
Yeah. So it's just slightly lower. I'm gonna have to
It's a little too much.
It's a little too high. Let's see. That's good.
Yeah, that's great.
Yeah. All right, so that's how you do it. So now for the next step of method 3, Archimedes method, we're going to carefully and gently lift up this solid, carefully placing our beaker of water here. So it's on this stand so that this mass can still move around. We're not recording the mass of the beaker. We're going to gently lower the mass into the beaker of water, and you'll notice that it's not touching the bottom and it's fully submerged.
How frustrating would it be if it slipped off the string right now? So we gotta be careful.
Yeah, it'd be pretty frustrating. So, and then as you notice now that the scale now reads that the mass is too heavy, so we have to lower these balances. So I'm going to do that now.
Gently stand.
Yeah. So at 40, this mass is too heavy. At 30, it now moves up, so we know that at least it's in the 30s. So let's try moving this to 7, 6. Oh, let's try 7.
Move your lowest one all the way to the left, maybe.
Oh yeah. Don't forget that. Let's try halfway. Just it's a little bit.
Tiny bit.
Yeah. Just a little bit more.
Nailed it.
That's good.
I think it looks good to me. From this angle, at least. How
No,
about
it's
straight on?
From straight on, it's a little bit.
Oh. That's why your angle where you're standing really matters.
Yeah. You want to look at it like you're looking at a meniscus. I think that should be good.